Okay. So in the last lecture, we introduced the notion of basis vectors. You have already seen the notion of basis vectors in your course on vector algebra in your high school. Basically, unit vectors are vectors of magnitude 1, length 1, and whose direction help us to orient the vectors in a 2 or 3 dimensional space properly, right? So any vector can be decomposed into a linear combination of the basis vectors. For example, one example is the vector on top of this page, a equals 2i plus j. So this equation, as you very well know, implies that I'm orienting a vector with an x component of 2 and a y component of 1. And the length of the vector can be calculated by the usual process, which we will talk about today. Okay. So today I want to continue with this idea of basis vectors. One thing that we said yesterday was that there is nothing sacred about the choice of basis vectors. So I can always find another set of basis vectors in the same two-dimensional space, which are orthonormal. Orthonormal means the unit vectors are mutually orthogonal and the length of each unit vector is normalized to 1. So another example is what is in the boxed equation on the page that is visible to you. Ex is I plus j over root 2. And Ey is I minus j over root 2. If you calculate Ex dot Ex, you will find that it is equal to 1. And Ey dot Ey will also be equal to 1. So they are normalized to unity. And you will find that Ex dot Ey is equal to 0. So in that sense, they are orthogonal to each other. Okay. So we will use the term orthogonal in a general sense, but orthogonal, I will warn you, cannot always be thought of as perpendicular in this same way that we think of perpendicular vectors in a three-dimensional space, because we would be extending this concept to multi-dimensional spaces and also infinite dimensional spaces. And we will also talk about orthogonal vectors in infinite dimensions. So it's very hard for us to picture, because our brains are not programmed to think about dimensions higher than 3, and even 3 is sort of stretching it, at least for me. You cannot think of vectors that are perpendicular in this higher dimensional space, but we still use the notion of orthogonality. So the notion of orthogonality you have to make a switch from thinking about it geometrically as two perpendicular vectors to thinking about it sort of algebraically as simply the dot product. It's a specific rule for dot product defined as a dot product of two vectors being equal to 0. Okay, so this is the way in which you should approach the notion of orthogonality of two vectors. So I asked you to work out the vector A in the Ex, Ey basis, and I hope that all of you had fun doing it. It is not a very terribly difficult exercise. You will find that the vector A can now be written as square root of 2 plus 1 over square root of 2 times Ex hat plus square root of 2 minus 1 over square root of 2 times Ey hat. So in other words, the important lesson here is that the components of a vector are unique once you specify the basis. Okay, the components of a vector are basis dependent. So in the ij basis, I can write my a vector as 2i plus j, and in the ex ey basis, I can write the vector as square root of 2 plus 1 over 2 and square root of 2 minus 1 over root 2. Okay, so this is the important thing that you have to understand. So I will now move on to today's class, but before I move on, are there any questions about any of the things that we discussed last time? Any questions, any comments, anything that you found a little difficult to follow? Okay, so I'm sharing my screen again. So once this gets done, we will get started. Okay. So in the last example, we needed precisely two basis vectors to describe the linear vector space that we were in, right? So the number of basis vectors that you need to describe any vector completely in the linear vector space is called the dimensionality of the linear vector space. So the number of basis vectors that you need is called the dimensionality of the LVS. So in the previous example, uh, where you need ij or equivalently ex, ey, the dimensionality of this vector space is 2, because to describe any vector in this linear vector space, I would need 2 basis vectors. Okay. So once you fix the basis vectors, the components of a vector in that LVS are unique. This means that once I fix my basis vectors to be ij or exey, I know that the components of my vector are 2, 1, or whatever it is. But the basis vector itself is not sacrosanct. I can always find linear combinations of basis vectors to form another set of orthonormal basis vectors. But once I choose one particular set of basis vectors, then the components of all my vector are fixed. So this is also something that you probably already have seen before. Okay. All right. So with that knowledge, let us move on to how to construct basis vectors. But before that, let me remind you that just like you should think of the notion of vectors as, not just directed line segments in space, but any set of objects that satisfies all the 10 axioms that we laid out the last lecture. The same goes true for basis vectors. For example, yeah. Suppose if I have a linear vector space in which the vectors are a set of all 2 by 2 matrices with 0 trace. Okay. So I can have any 2 by 2 matrix with 0 trace. Okay. Now, if I add 2 matrices with 0 trace, I would again get a matrix with 0 trace. And if I multiply a matrix with 0 trace with any number, I would again get a matrix with 0 trace. So you can actually easily satisfy yourself that a set of all 2 by 2 matrices with 0 trace satisfies all the axioms that we laid out. So this can be thought of as a linear vector space. So now we can ask, what is the dimensionality of this linear vector space? Okay. Now we should be a little careful, because the dimensionality of the linear vector space has nothing to do with the dimension of the matrices. Okay. The matrices are 2 by 2, right? So 2 rows and 2 columns. I can also construct 3 by 3 matrices with 0 trace, or 10 by 10 matrices with 0 trace. But the dimensionality of this vector space, in which the basic vectors are 2 by 2 matrices, is not 2. Okay, it is actually 3. The basis vectors, it turns out, for this linear vector space, one choice of basis vectors are the 3 Pauli matrices. Okay, so somebody is joining, so I'll admit him. The 3 Pauli matrices are given by, if you have not seen them before, the 3 Pauli matrices are: sigma 1 is 0, 1, 1, 0. Sigma 2 is 0, minus I, 0. and sigma 3 is 1, 0, 0, minus 1. Okay, these are the three basis vectors. So what do I mean by the notion of basis vectors in this context? So I simply mean that any 2 by 2 matrix with zero trace can be expanded in terms of sigma 1, sigma 2, and sigma 3. Okay, so let us so what does this mean? This means formally that just like in Cartesian system, in Cartesian coordinates, if I have a vector, I can write this vector as a linear combination of I, J, and K, right? Just like that, in this space of 2 by 2 matrices, I can write any 2 by 2 matrix with zero trace as something times sigma 1 plus something times sigma 2 plus something times sigma 3. Okay, see the formal correspondence. So any matrix with zero trace forms an example of a vector in this linear vector space. So this corresponds to the A vector that we have in Cartesian coordinate system. Just like I, J, K form the basis vectors, sigma 1, sigma 2, sigma 3 form the basis vectors in this space. Just like AX, AY, AZ are the components of this vector, this, and this are the components of this guy. Okay, let us satisfy yourself that this is indeed true. I'm not making it up. So let us take an example of a 2 by 2 matrix. Of course, I can take any matrix with zeros and something here and something here, but that will be a little simplistic. So in general, I can take any matrix of this form, right? This has zero trace. A minus A is 0. This can be anything. So I'll put something like B and something like C here. Okay. So you can actually easily satisfy yourself that this can be written in terms of sigma 1, sigma 2, and sigma 3. The easiest thing to check is sigma 3. So notice that to generate the 1, 1 component and the 2, 2 component, you have to have sigma 3 because sigma 3 has the 1, 1 component and 2, 2 component. So this has to be of the form A times 1, 0, 0, minus 1, right? And then you have 0, B, C, 0, right? Now there is no I here, so this can be written as A times 1, 0, 0, minus 1 plus some combination of sigma 1 and sigma 2. So some, let us say K1 times sigma 1 plus K2 times sigma 2. K1 times sigma 1 and K2 times sigma 2 should generate for me this 0BC0. Okay. How can that be? Well, let us work it out. What is K1 times sigma 1? K1 times sigma 1 is 0 K1, K1 0 plus K2 times sigma 2 is 0 minus IK2, IK2 0. This plus this has to generate whatever is remaining because the diagonal elements can only be generated by sigma 3 because sigma 1 and sigma 2 don't have any diagonal elements. So I have taken care of the diagonal elements. So off diagonal elements has to be generated by either sigma 1 or sigma 2 or some combination of sigma 1 and sigma 2. So how will this work? So let us take the most general combination K1 sigma 1 plus K2 sigma 2, and this has to be equal to 0BC0. Yeah. So what is this? So this tells me that 0 K1 minus IK2, K1 plus IK2 0 equals 0BC0. Okay. So these are two equations and two unknowns. This tells me that K1 minus IK2 has to be B and K1 plus IK2 has to be C. So if I simply add these two, I get K1 equals B plus C over 2. Similarly, K2 has to be something else. So you can substitute it in there and you can write this general matrix A, B, C minus A 2 by 2 matrix with zero trace as something times sigma 1 plus something times sigma 2 plus something times sigma 3. Okay. So your idea of vectors don't have to be confined to simply three-dimensional directed line segments in space. Any set of objects that follows the axioms of LVS um, are proper vectors, and similarly basis vectors are similarly any set of objects that can be used such that any vector, any object in this space can be written as a linear combination of these basic objects. Okay, so there is a question, how does sigma 3 have zero trace? Trace means leading diagonal has zero elements. That is not true. That is one example of a zero trace. The trace simply means the sum of the diagonal elements. Okay, so the sum of the diagonal elements, if it is zero, the trace is zero. So for sigma 3, the sum of the diagonal elements is 1 minus 1, which is 0. So any matrix that has a sum of diagonal elements equal to 0 is called a zero trace matrix. For example, 3, 2, 1, minus 1, minus 2, 0, 1, 4, minus 1 has zero trace. Okay, because the sum of the diagonal elements is 3 minus 2 minus 1, which is 0. Okay, so I hope that answers your question. Any other questions at this stage before we progress?
Hello?
Yes.
Sir, I'm able to understand the mathematics, but I don't get like I know there is three dimensionality, but this 2 by 2 matrix, what does it represent?
Okay, so this 2 by 2 matrix can represent anything. So for example, in physics, these 2 by 2 matrix represents what are called spin states. Okay, so for example, all of you have seen, or at least have, yeah, well, at least heard that an electron has spin up and spin down. Agreed?
Yes, sir.
Okay. So what is spin up and what is spin down? Of course, I will be doing a more complete job of explaining spin one and spin half to you later when I talk about angular momentum, but this is just to give a flavor of why this can be useful in physics. So let us talk about electrons. Electrons have, let us say we have this, we say they have spin half, right? So spin is a vector. So spin is a vector, right? So spin has three components, we say. There is one component, there is a two component, and there is a three component. Okay, some people say Sx, Sy, Sz. Some people say S1, S2, S3. Remember that if I say Sx, X, Sy, and Sz, I don't in any way mean XYZ coordinates. It is just three different vectors and three different components, and one way to characterize them is to write them as Sx, Sy, and Sz. Okay. So the first component of spin is represented by this matrix. So what is this matrix? This matrix is for spin half case, it is sigma 1. The second component of spin is sigma 2. The third component of spin is sigma 3. Okay. So in the spin half case, the three Pauli matrices, sigma 1, sigma 2, and sigma 3 represent the three components of the spin vector. So I will be using this example over and over again when I talk about operators and things like that. When I complete my discussion of LVS, hopefully the physics, at least for this particular example, should be apparent. Okay. So there is two different kinds of objects when you talk about linear vector spaces. There are vectors and there are stuff that pushes, pulls, and throws around these vectors. The stuff that does the pushing, pulling, and throwing around these vectors, they are called operators. Okay. So in that sense, the sigma 1, sigma 2, sigma 3, which I denoted as basis vectors in the linear vector space, can also be termed as operators. So this can be a little confusing initially, but hopefully it won't be confusing as we go along in this course. So the correct interpretation of sigma 1, sigma 2, sigma 3 is that they are operators in a linear vector space corresponding to the three components of a spin half particle. Okay, this is the essential physics of Pauli matrices. Of course, there's a lot to unpack in this statement, which we will do over the course of not just this first course, also the second course on quantum mechanics. But for now, I'm introducing the Pauli matrices in a slightly different way. I'm claiming that, yes, these matrices can also act as vectors in the three-dimensional space, act as operators in a specific dimensional space, but they can also be termed as basis vectors for a different linear vector space. So I will give you these two examples of linear vector spaces. Again, my sharing is causing a problem, so I'll come back to this. So, okay. So in this example that I talked about, the three matrices, the three 2 by 2 matrices that I talked about are basis vectors. So I hope it is clear that any 2 by 2 matrix with zero trace can be expanded as a linear combination of these basis vectors. Again, there is nothing sacred about this choice of basis vector. I can do any linear combination of these basis vectors and choose another set of basis vectors that are also orthonormal. So I should also prove that they are orthonormal. I will prove them later. But these same matrices can also serve as operators in a different linear vector space. So this is a three-dimensional linear vector space. So this is a 3D LVS. Okay, but consider a 2D LVS, which is a different linear vector space composed of the usual vectors. Okay, composed of vectors that you can think of as column vectors. So I can think of column vectors, let us say some V, which has components V1 and V2. Okay, in this two-dimensional linear vector space, the Pauli matrices can push or pull these linear vectors. How? The Pauli matrix sigma 1 can act on V. How does it act? It gives 0, 1, 1, 0 acting on V1, V2 equals V2, V1. So sigma 1 has the job of interchanging the two components of this vector. Similarly, sigma 2 does something else and sigma 3 does something else. So the notion of matrices is extremely important in linear vector space because they can serve as two different things, even though we would primarily be using them in this language. So in this language, the sigmas are called operators. I'll come to the operators later. So primarily I'll be using matrices as operators, but you should remember that matrices are not just operators. Depending on the kind of linear vector space that you're talking about, matrices can also be basis vectors, because if the objects in the linear vector space are matrices, then obviously the basis vectors in this linear vector space are also matrices. If the objects in a linear vector space are vectors of this form, V1, V2, then matrices in this linear vector space act as operators that do something to the vectors. So there is two different ways you can understand these matrices. Okay. So I am introducing the first way. We will come to the second way of introducing them as operators later in this course. Any questions? Is that clear? Any questions or comments? Okay. So we will, for now, we will set aside this notion of operators and we will talk primarily about basis vectors. We will come back to the notion of operators a little while later. Okay. So how should my basis vectors be? So can any set of, for example, in the original two-dimensional vector space, suppose I have, let us say, I vector I cap and j cap, right? How do I know that it is just I cap and j cap, and how do I know that there is not a third basis vector, some L cap? Okay, so there should be some rule that tells me what is the number of basis vectors I need, and whether if you give me a set of basis vectors, I should be able to see if many of these are not necessary. Okay, suppose if you give me a set of 4 basis vectors to describe a two-dimensional linear vector space, I know that there is something missing here. I know that we don't need 4 basis vectors to describe a two-dimensional linear vector space, because by definition, the dimensionality of the linear vector space is a number of basis vectors. So if you give me 4 basis vectors, I know that I can throw 2 of them away. So what is the mathematical property that helps me to throw away some of the basis vectors and choose just the right number of basis vectors to describe a linear vector space with? This notion is called linear independence. Independence. So this sharing is turning out to be a nightmare. I should try to see what's wrong. Okay. So what is linear independence? Suppose if I have a set of basis vectors. So let me first give you an example and then tell you what the actual property is. So let us say that to describe the two-dimensional linear vector space that we talked about, ij, I give you a set of three basis vectors and I claim that you need I, j, and I plus j over root 2 to describe this linear vector space. Okay. So how would you be? So if you knew nothing about basis vectors, obviously you know that the third vector is not needed. But suppose if you knew nothing about it, the way you can say that my claim is bogus is by saying that no. This third vector is nothing special. This third vector is simply a combination of the first vector and the second vector. So if I call this third vector some e hat, this e hat is simply 1 over root 2 times the first vector, which I will call E. So let us call this E3, E2, and E1. The third vector is nothing but a linear combination of the first two. So the third vector gives me nothing new. Okay. So if in a set, I have one vector which can be written as a linear combination of the other vectors, then that particular vector is unnecessary as a basis vector. I can throw it out. Okay. So by this act of eliminating, if I give you a general set of basis vectors and claim that you need this many number of basis vectors, you can see how many of those vectors can be written as linear combination of the other vectors. And every vector that can be written as a linear combination of the other vector is not a unique vector, so we can throw that vector out. Okay, so this gives us the idea of linear independence. Suppose if we have a set of vectors xi, okay, I can be anything, 3, 4, 5, 6, 7, 8, whatever it is. Suppose if I form a vector equation of this form, aixi, okay, equal to 0. Then if I'm able to write down a solution for this equation, then the vectors xi are linearly dependent. If the only solution of this equation is all ai equal to 0, then the vectors are independent. So let's call this equation 1. If the only solution of equation 1 is all ai identically equal to 0, then the vectors xi are linearly independent, which means that not one vector can be written as a linear combination of the other vectors. So this is basically whatever I said here in the first half in a mathematical notation. For example, in the first equation, if I take I, j, and I plus j over root 2, right? So suppose if I write it as a column vector, I can write as 1, 0, j I can write as 0, 1, and I plus j over root 2 I can write as 1 over root 2, 1, 1. This is the set of the basis vectors here, right? This is the same in column vector notation. If you have any difficulty understanding this column vector notation, please stop me now and ask. Okay, I will answer and then move on, because this, to go from this and this is very important. I'll be using both these notations primarily, but as the course progresses, I will be predominantly using the second notation, And then after that, I'll be using an abstract notation for basis vector some ei ket. Okay. All right. So this the notation 1 0 simply says that this vector has component 1 along the x-axis and component 0 along the y-axis, which is precisely I hat. This notation 0 1 says that this vector has component 0 along the x-axis and component 1 along the y-axis, which is precisely j hat. And this is some linear combination of the two. Okay. So for this set, let us write down this equation ai xi equal to 0. So I will write down a1 times 1 0 plus a2 times 0 1 plus a3 over root 2 times 1 1 equal to 0. This is this equation ai xi equal to 0, right? Okay. So the question is, are there solutions for this equation or no? Obviously, there is a solution for this equation, right? Excuse me. So I can rewrite this equation as a1 times 1 0 plus a2 times 0 1 equals minus a3 over root 2 times 1 1, which tells me that a1 is minus a3 over root 2 and a2 is also minus a3 over root 2. So since there is a solution for this equation where I can express a3, I can express a1 and a2 in terms of a3. A3 is unnecessary. I might as well throw away a3, or equivalently, I can throw away the last vector I plus j over root 2. Okay, so this is the notion of linear independence in a very simple setting. So in general, if I give you a set of vectors, you should be able to tell me if the vectors are linearly independent or not. The last thing that I want to talk about today is the notion of norm and inner product. This is a very important notion in quantum mechanics. In fact, the notion of inner product is central to quantum mechanics. So let us talk about this in the context of, again, simple vectors, and then we will extend this notation to the bra and ket. Okay. So let us, so norm and inner product of vectors. So let us take a very simple example of A equals AXI plus AYJ plus AZK. And suppose if I ask you, what is the Z component of this vector? What is the detailed mathematical procedure that will help you tell me what is the Z component of the vector? If I phrase the question that way, you will laugh at me because you know that the Z component of this vector is just AZ, right? You don't have to do any calculation. You can just look at the vector and tell me what the Z component of the vector is. There is no detailed mathematical calculation that you would need to do. So you would think I'm being silly. I am being silly, but notice that the reason you can extract this with very little difficulty is because you're so used to the mathematical idea behind it. The exact way in which you extract the Z component of this vector is by actually projecting out the component of A along a particular direction. Suppose if I ask you what is the component of A along the y-axis, you have to have a mathematical procedure that helps you to project out the component of A along the y direction, or project out the component of A along the x or z directions. The way you do it is by taking a dot product of this vector. Suppose if I tell you suppose if I ask you what is the z component, in your mind, you do this, A dot k hat. And since k dot I hat is 0, k hat dot j hat is 0, and k hat dot k hat is 1, this immediately gives you a z, right? So this act of projecting out the z component is achieved by the dot product. The dot product of two vectors in general gives you the direction of the second vector along the first vector. So suppose if I have two vectors, A vector and B vector, and if I say what is A vector dot B vector, I am asking how much of B lies along the direction of A, or equivalently how much of A lies along the direction. Okay. Typically what I do is I take K hat dot A vector. That is what I do. Okay, that is equal to AZ. So whatever vector I want to project out, I take it first and then dot it out with the second vector. Excuse me. Okay. So obviously, if I have, if A dot B is equal to 0, I claim that there is no part of B that is lying along the direction of A. Okay. So there is no amount of B that is lying in the direction of A. So A and B are completely perpendicular to each other. So we claim that A and B are orthogonal vectors. They're perpendicular to each other in the simple three-dimensional Cartesian system, or in general, they are orthogonal to each other. Okay. So this is the notion of orthogonality. This is the notion of dot product, and this is the notion of projection of vector along different components. So we will extend this notion to to arbitrary number of dimensions with our crazy notation for vectors. So I will write a vector alpha in some linear vector space which has basis vectors ei. So how will I write this alpha in this basis vector? I will write this alpha as some linear combination of the basis vectors, right? So let us assume that there is a finite dimensional linear vector space with dimensionality n. So I need n number of basis vectors to describe any vector in this basis. So I can write this as sum over I, ai, ei. So where repeated indices are summed over. So this is called the Einstein summation convention. Whenever I write ai, ei, I don't even have to write the summation. So I can as well write this as ai, ei and leave the sum for your imagination. This is called the Einstein summation convention. But I will not be following this religiously in this course. But if you look at any book that does this, you have to understand that there is a sum over I. Okay, all right. So how will I extend the notion of vectors normalized, basis vectors normalized to unity, or basis vectors that are orthogonal to each other? So notice that if I want vectors that are orthogonal to each other, I dot j has to be equal to 0. Okay, all right. So I need a way of multiplying two vectors in some sense, right? The dot product basically is a rule of multiplication of two vectors. But how would I multiply a vector? So suppose if I only know about column vectors, so let us say that I write this vector alpha. Instead of writing it in this way, I can write this as a column vector a1, a2, a3 up to an, right? Just like I wrote I vector as 1, 0 and j vector as 0, 1 and things like that. I can write this alpha as a n-dimensional column vector with entries a1, a2, a3 up to a in the components of this vector. If I only know about a column vector, I cannot multiply vectors because I cannot multiply two column vectors to get another column vector. Okay. The multiplication, of course, this is called the direct product, and this is a different beast altogether. We will talk about this much later when we talk about angular momentum. But notice that the dot product of two vectors is a number. So I need a way of multiplying this vector with some other vector that gives me a number. So if I have a column vector like 2, 3, the only way I can multiply another vector with it to get a number out is if I also have a row vector like 1, 5. Because a row vector times a column vector is a number. In this case, it is 2 plus 15 equal to 17. So if I only have vectors of this form, which can be thought of as column vectors, I cannot really define dot products. I need vectors of a different form. I need also vectors of this form. Okay, so that I can take this vector and multiply it by this vector to get a number out. So this idea of finding a different vector, not just a ket alpha, but a different vector that can actually multiply this vector to give me a number out, leads us to the definition of what is called the dual space. A dual linear vector space. To every vector alpha, there is a corresponding, there is this DC is called dual correspondence. This is a symbol of Sakurai. There is a corresponding row vector, which I will call by this notation. So if this guy is A1, A2, AN, a column vector, this guy is a row vector with A1, A2, A3 up to AN. Okay. So just like I can multiply a row vector with a column vector to give me a number, I can multiply this object on the right with this object on the left to get a number. This object on the right is called, as you know, a ket, and this object on the right, as you probably already know, is called a bra. Okay, so the multiplication of a bra with a ket to form a bracket gives me a number. Okay, this is Dirac notation. So the way I get a number out, I actually do the dot product, is if I don't restrict myself to just one linear vector space. With just one linear vector space composed of purely column vectors, I cannot define dot product. So I also need row vectors. But notice that row vectors and column vectors cannot coexist in a single linear vector space. Why? Because in a single linear vector space, you need a single set of basis vectors with which I can describe all the vectors. But the row vectors, so for example, if you take a simple 2D example, right? The two basis vectors I need in this space are 1, 0 and 0, 1. I can describe any ket vector of the form AB as A times the first basis vector plus B times the second basis vector. But I cannot describe a vector of this form in this basis vector with this basis vectors. Why? Because no row vector can be written as a linear combination of a bunch of column vectors. So I have to invent a new space, a new linear vector space that is dual to this linear vector space. Okay. This dual linear vector space contains every single vector in the other space, but with transpose. So every single column vector there can be thought of as a row vector in this linear vector space. So in this linear vector space, I also have basis vectors. The basis vectors are 1, 0 and 0, 1. So that anything can be written as a linear combination of these two basis vectors. Just like this guy and this guy are the basis vectors in the ket space, this guy and this guy are the basis vectors in the corresponding dual vector space called the bra space. So with just ket vectors, our language would be incomplete. Because ultimately, you see, we need a way of getting numbers out in physics. That is a very simple way of stating this. In quantum mechanics, these numbers are called probability amplitudes, as we will talk about a little later. But ultimately, experimentalists don't measure vectors, right? They tell you that the magnetic moment is this number. So whatever theory you invent, whatever theory you concoct, this theory should have a set of rules that would give you or predict what these numbers are. So ultimately, in a physical theory, you have to have a way of getting numbers out. The objects in this physical theory can be as complicated as possible. So in quantum mechanics, these are linear vectors. In electromagnetism, you will have field strength tensors, F mu nu, right? But ultimately, the electron magnetic moment is not a tensor, it's a number. So classical electrodynamics is basically a set of rules that tells you how to calculate these numbers, right? In general relativity, you would have Einstein tensors, but ultimately you would have the precision of Mercury is a number. So you have to have a set of rules that tells you how to calculate this number. So the objects in a physical theory can be complicated, but all these theories should tell you a way of calculating numbers that are the results of experimental measurements. Okay, so this is the reason why the notion of dual space is very important, because if I only have vectors, I cannot get numbers out of them. I need to have the bra vectors along with the ket vectors so that I can multiply these two and get the number out. So today I will stop at this stage, and tomorrow I will continue and tell you the uh, multiplication rules in the bracket notation, and we will finish our notion discussion of basis vectors and inner products, and then we will move on to, we'll at least get started on the idea of operators if we have time. Okay, that will be the rough plan for tomorrow. So let me stop here at this point because we have covered quite a bit of ground, and let me ask if there is any questions from any of you. So I will stop the recording at this stage and we will take questions.